Hello everyone, my name is Mohsin Raza, and I'm representing here TPC component. I'm also PhD student at Metalliska Högskola. I will present about a continuity of our previous work that we have been doing with Sverige Svecast and GKN Aerospace and Nova Fluent System for last 4 or 5 years. And here we have another project that we are working now, and it's development of lightweight components for jet motors. So in this whole project, the main theme is to be able to produce thin-walled components, so that we can reduce the overall weight of turbine, which means that we can reduce the fuel emissions, hazardous emissions, and also lower consumptions. So the focus is to have thin-walled components. So that's why TPC is involved in this project. We want to reduce the minimum costable thickness. Right now in investment costing process, the minimal thickness that we can produce is around 2 millimeters, 2.5 millimeters. If we want to go below that thickness, then we have a problem, because then it becomes difficult to fill the mold, because there is a back pressure, surface tension effect, then metal mold reaction. So metal cannot go deep into the thin cavity. So that's the problem. So we are stuck with the limit of 2 millimeter cost sections. So what we want to do, we want to challenge that limit, and we want to we want to produce thickness like 1.5 maybe, or maybe less than that, if we can manage to achieve that. For that, we need to know how metal behave in the mold. So if you see I'm saying that method for wall thickness reduction, how we can do that, what are the limitations that we face during casting process? Is it the melt temperature that is not good enough to fill that cavity? Is there is reaction between metal and mold? Is there some kind of surface tension happening there? Is that alloy has different properties, they don't go very well into the mold? Is there any kind of flow rate influence? If we have a higher flow rate, then can we get better filling? Can we get longer fill in the thinner sections? So the purpose of this project is to identify all those parameters that affect castability in thin sections. But we are not stuck with only that point. We are not just investigating the parameters. We are also trying to influence those parameters. And influencing means that we have investigated how vibration, if we apply vibration on the investment costing mold, how it can help to get more fill in the mold. Or maybe we can have a partially induced pressure that also can help to have more fill in the mold. When we have done this thing, if we are successful in that, then we need to have a tool so we can simulate what we have done, or the parameters that we have investigated, or they replicate in a simulation tool. The methods that we have invented for making thin casting, can they be replicated in the simulation tool? So for that, we have as I showed in first slide, we have a Nova Fluent system. They are working with this with us in this project. So they are working on the developing simulation methods, so we can simulate our process, the thin wall component process. After we have all the simulation, then we have all the parameter investigated, then we want to produce a demonstrator for a system producer like GKN Aerospace. They have a system, they have a turbine, they want component in thin section, then they assemble them into full component, into a turbine, into full system. So we want to produce a demonstrator for them. And then also for the academia, we want to produce a course and a scientific publication out of that. How it will impact the industry? We will have a lightweight aircraft engine. We will have less emissions for environment. Since there are component manufacturer, there is a system manufacturer, there is a research institute, Sverige Svecast. So we will have a strong Swedish supply chain that we are aiming at. And then we will have a new market segment where we can claim that yes, we can produce thicknesses less than 2 millimeter, which is kind of a new limit for investment costing. Let's say we are successful in 1.5, then it's a new limit. So it's a new market segment for turbine components. And then for both, as I said, that we want to increase the knowledge for academic, so we can say that we can publish something, and we can prove that these concepts are based on some science. So what is our strategy in that project? This is, in the first picture you see a hub, complete hub. So we took apart from that hub. This geometry resembles a section taken from there. This is a challenging geometry as it has 1.5 in the center, and then we have 2 millimeter here. And this is 200 millimeter long and 170 millimeter wide. We picked this geometry because we don't want to fill this geometry. This is a test geometry. We want to have a kind of what is called interrupted casting, where we don't fill the casting. We get some kind of unfilled area in the middle. And then from that, we need to calibrate our simulation. So we need to see that, can we replicate this casting into the simulation model? So for that, we pick this geometry, which is challenging, which is not possible, actually not easy to cast. This is just for the calibration. Once we have a simulation calibrated, then we will go for actual demonstrator casting. This is a hub sector. This is taken from here. So these all hub sector will be welded together, and then they will form a complete hub for a turbine. So the implementation strategy that we used in this project, we have a simulation tool, that is NovaFlow and Solid, and then we have a costing trials. In costing trial, we have different things to investigate. We have a gating effect, how the gating, if you I think it's a feeding method, how you fill the geometry, how it affects the costability of thin section, how Li has different effect. For example, Rene 220, we have will have learned that Rene 220 have a better fluidity than INCO 718. So we investigated 3 different alloys, is Rene 220, INCO 718, and CM939, to see which alloy has better costability. And we also investigated that this alloy should have a aerograde specification. It's not just like any alloy. It should have a high creep strength. It should have a high thermal behavior, and it should perform well at high temperature, like in turbine. Then we have foundry variables like casting temperature, shell temperature, how much shell you have heated, how was the pouring rate, is it slow pouring rate, is it fast pouring rate, depending on the furnaces that you use. And also casting variables. We have learned in this project that since casting methods are like very manual method, they are not automized methods. So there is also human involvement. We have seen that people, if we change operator, we get different fillability in thin section. So it depends on how the operator behaves during the casting. Is it very fast, he's very slow, he's calm, or he's splashing in the mold, or he's taking care of well-maintained stream in the mold. So all these things affect. So we noted all these parameters, and then we replicate those parameters in the simulation setup, and then we have some adjustment in the software. We can fine-tune the software we have a material characterization. By that we put for example, Rene 220 is not, you cannot just go in literature and just pick up the values from literature and put in the software, because all the melts, all heats that we get from supplier, they can have different thermal properties. So what we did, we characterized material. For example, INCO 718, I see Jönköping University here. We did some experiments there in Jönköping, and we did thermal diffusivity, thermal conductivity, density measurement for 718. Then we have CLF, P and CLF. This is critical liquid fraction and critical liquid pressure. These are some parameters that we can tune in the software to get the calibration, to make a match between actual costing and the simulation. Similarly, gravity effect and alloy density effect and heat transfer models that we can adjust to get a calibrated simulation. Once we see that our test geometry and simulation are calibrated, they show the same results, then we go for demonstration. As I showed in the previous slide, we have a demonstrator costing. This is a demonstrator. So we produce that costing, and then we send them to the component manufacturer, so they can weld, they can join them, weld them, and make a costing. So this is the just scope of project. So where we are right now, we have done material characterization. We have for RNA 220, for CM939, for INCO 718, we have a thermal data that we have introduced in the software. We have investigated all the foundry parameters, relevant foundry parameters, for example, how the shell temperature affect castability, how mold temperature affect, how pouring rate affect castability, and how the human involvement in the process make variation. And these all results will be published in a scientific journal, that publication that's coming in hopefully in the May. So we have set the boundary condition. We have simulation. Now you see this. This is a simulation that we have performed after doing all these adjustments, and there is the actual costing that we see. I see my very senior professor here. Hi. So these are now calibrated. From this simulation software, we have almost done this calibration. Now we are going to the next stage, where we will produce a demonstrator for actual hub, and we are also working in the same time on the course material and publication. So what is coming next? In March, we have planned for this hub casting, these hub sector casting. These are ready in a wax shop right now. Yes, please. Okay. And then we have a weldability test in a GKN that will send this part to the GKN. We will have a evaluation and verification, and then we will qualify for we will do the all quality inspection for the first piece, and we will submit the course material and publication by end of May. Yeah, that's it. Thank you.
As I understand, the project is delayed. Does happen something? It should end it in 19.
Yeah, I think we are 5 months late.
Yes, 5 months late. That's correct.
Yeah.
But I take this question: what about the implementation? If it is good results, what does GKN say, or someone else who want these results?
If the results are good, what will be the advantage? For example, if this hub sector is right now is, I think, 2.7 millimeter wall thickness. Yes. So if we learn how we can reduce this wall thickness, and we show that by producing this demonstrator, like maybe in 1.5. For example, this geometry is like right now challenging 1.5 limit. So if we produce a thin hub sector, and that can be put together in the shape of this big hub, this is a demonstrator. This is a proof that yes, wall thickness can be reduced if you have a better understanding of your process, if you have better understanding of your parameters that controls the fluidity. So like these are the identifying the best boundary condition that can help in reducing wall thickness. So if we have all this knowledge, then I think in the next phase, we can go for producing thin walled. Maybe right now we are 2.7, so the next time maybe we can challenge 2.2 millimeter in this kind of hub sectors, and that's why we have a system manufacturer, GKN, with us. They want to get a proof from us before they can start. Mm-hmm.
So, is there any small comment from the audience? If not, I suggest we thank Mohsin once again.